I'm going to talk about IOThread Virtqueue Mapping. IOThread Virtqueue Mapping is a virtio-blk feature that was added in QEMU 9.0 that helps scalability of virtio-blk. So virtio-blk was optimized over the years, but typically with a workload that is running on one CPU, submitting I/O on one CPU, doing that as fast as possible. And the bare metal overhead, if you compare bare metal and you compare the virtual machine, that's what we focused on. But on larger systems, larger VMs that have many vCPUs and a workload that's actually submitting I/O requests concurrently across all those across all those vCPUs, the overhead of virtualization is significantly higher than what you see with just one vCPU. So some of the numbers that I saw when we began this work was maybe 20% virtualization overhead, maybe even 30%, so way too high. And so that was something we wanted to optimize. And this is very important because nowadays virtual machines tend to have a lot of vCPUs, right? So this is not a high-end rare case. This is a common case nowadays. So we need to fix this. So let's start by looking at how the virtio-blk device is designed and how it handles scalability. Virtio-blk is a multi-queue device. So it's possible to have many virtqueues on your virtio-blk device, and then each vCPU can use its own dedicated virtqueue. And the advantage of doing this is that the guest driver doesn't have any contention when it's submitting or completing I/O. It doesn't need to communicate or take locks in order to share just one virtqueue. Instead, each vCPU has a dedicated virtqueue that's operating independently and concurrently with everything else that's going on. The other advantage of multi-queue is that completion interrupts can be directed straight to the vCPU that submitted the I/O, which is where the application is running, where the caches are hot. So that's the best place to be. If you didn't have the ability to direct the completion interrupt to the right CPU, you would have to send it to an arbitrary CPU. And then that CPU would have to notify the actual CPU where the application is about this completion. And that adds latency. So this is very standard stuff for hardware design. Network cards have been doing it for a long time. NVMe, the NVMe PCI interface also is multi-queue in this way. And in fact, QEMU enables this by default. When you launch QEMU and you launch, say, a 16 vCPU VM, you don't even need to specify anything. Your virtio-blk devices will automatically have 16 vCPUs. So why does SMP performance still suffer, right? So QEMU implements this, it's all there. But why are we still slow when we have big VMs? So let's look into that. The answer is in how QEMU actually processes those virtqueues. The virtio-blk design itself is good, but what's happening in QEMU when we process a virtqueue is that in QEMU, a single thread handles all of the virtqueues for a single virtio-blk device. So that's where you see this kind of funnel, this bottleneck shape, if you look at the diagram. So if we have 4 vCPUs in our guest, on the host side, we actually still just have one thread that is processing all of those virtqueues. And it's kind of unfair because imagine you have 4 vCPUs that are all adding as many I/Os as they can as quickly as possible. On the host side, you only have one CPU that's trying to process all of that for them. So how is it supposed to keep up? So that's kind of the hypothesis here. When I started this work, the idea is that this is a bottleneck. That's probably why we see these high overheads, 20% overhead or whatever the virtualization overhead is. And by the way, the work that the IOThread is doing in QEMU, it needs to parse the virtqueue requests. And then those requests go through the QEMU block layer. There you might have the QCAT2 image format. You might have other block layer features. And eventually the block layer says, okay, here's a buffer. Here's a logical block address. Let's submit this I/O. And it evokes a system call, maybe Linux AIO or IOUring. And it sends that to the host kernel. And then the host kernel goes and it does basically the same thing again. It has to parse Linux AIO or parse the IOUring request, sends it down the VFS and the Linux block layer. And then it sends that to the driver. So then the NVMe driver in Linux, for example, will submit that I/O. And then you take the reverse path up. QEMU will build the response, and it will inject an interrupt into the guest to complete the I/O. So that's a long path. There's a lot of CPU cycles doing stuff. And that also explains why this kind of bottleneck design becomes a problem, because as you overwhelm this one thread, it just can't keep up. So before we could actually solve this problem, I wanted to see what the performance improvement would be if we had this. And so what I did is I set up a simulation. I created a VM that had many virtio-blk devices that were all actually accessing the same image file, the same disk. Normally you wouldn't do that because you would corrupt your disk, but I didn't have a file system on it. I was just benchmarking the block devices from inside the guest. And what that allowed me to do is I gave each virtio-blk device its own dedicated I/O thread. So I was, in effect, simulating what if we had a dedicated I/O thread for every single queue, but I had lots of devices. And the result was that, indeed, you can get a lot more performance out. You can saturate your disk if you do that on a SMP guest, a guest with many vCPUs. Okay, so one thing I will point out is that on benchmark slides, when I have graphs, I have a GitLab link. You can go there. You can see my script, so you can get the command lines that I used. You can get the FIO benchmark results and an Ansible playbook to reproduce that. So if you want to dig into the details of the benchmarks, they're all there. Okay, so since simulating this showed that there's promise here, there's more performance we can get by doing this, we went ahead and did it. It's called IOThread Virtqueue Mapping. It was added in QEMU 9.0, so it's already there upstream, and you can use it. And effectively what it's doing is it's allowing you to take advantage of multi-queue on the host, not just in the guest. As you can see, it lets you assign vert queues to host I/O threads, and that way you can actually get this concurrency. Implementing this took a long time. Not the virtio part, but QEMU itself, in its history, it was single-threaded. So all the block layer code in QEMU has been single-threaded. And so Kevin Wolf and Emanuele Esposito and Paolo Bonzini and we worked on this for a number of years to make a truly multi-thread capable QEMU block layer. And Kevin and Emanuele presented the details of how they did that work in last year's KVM forum. So if you want to understand what locking changes they made and what problems they found, please check out their talk. I'm not going to go into that this time. What I am going to do is I'm going to show you how to configure this for virtio-blk devices. I'm going to talk about the performance improvements, show you my benchmarks. So yeah, that's what I will cover. So let's start with the libvirt syntax. So this is what you can use today. It's in libvirt 10. Peter Krempa implemented the syntax for us. And now you can add an IOThreads tag to your disks. And you can give it a set of IOThreads. You can tell it use IOThread 1, use IOThread 2. And those IOThreads will be round-robin allocated to the vert queues. So if your device has, say, 4 vert queues, because there are 4 vCPUs, and you want to give it 2 IOThreads, it will round-robin allocate them. So the first vert queue goes to IOThread 1. The second goes to IOThread 2. The third one goes back to IOThread 1, and so on. Because of the way that vert queues work, the vring shared memory data structure is a single consumer queue. So it's not the case that your vert queue can be serviced by any IO thread. Instead, you always just assign it to one. That way, we don't need to do any locking in the IO threads. Yeah, so that's how you configure it. I will show you the QEMU syntax as well. And in fact, we have some more advanced configuration you can do if you want. This is the QEMU syntax. In your device, you just add the IO thread mapping parameter, and you can give it an array of the IO threads you want to use. What I'm showing here additionally is that you can give it a virtqueues array, and you can actually assign on a per virtqueue basis. So if you want to go very fine-grained and assign individual virtqueues to individual IO threads, you can do that too. You don't need to round-robin allocate. You might be wondering, why do I want to do this? You probably don't. Most people don't need it. It's useful for devices where the virtqueues are differentiated, where they're not all equal. And in Linux, the virtio block driver actually has a kernel parameter or module parameter where you can reserve queues and use them as polling queues. So those queues won't use interrupts, and they'll work slightly differently. So that's an example of where maybe you'd want to assign them to a different IO thread. But in general, I don't think anyone needs this yet. I think that maybe for future devices like virtio-scsi, it will be more important to have control over this because you don't just have one type of queue. Okay, so that was added in QEMU 9.0 along with everything else. Before I go on, I do want to point out there's confusing terminology. There are QEMU's IO threads, and then in libvirt we also have IO equals threads. And those are two completely separate concepts. IO threads is what I've been talking about and what I mentioned. They're a feature in QEMU that allow the user to specify, okay, I want to have a thread, and then they can assign IO device emulation to those threads. They give you control over which threads are doing the IO emulation. IO equals threads is a different feature. It's a user-space thread pool. It's an asynchronous IO engine that QEMU can use. You probably won't use it though because you'd probably rather use Linux AIO, which typically performs better, or IOUring on Linux. But on other operating systems, you might use IO equals threads, and it's just a thread pool. It doesn't work very well with IOThread Virtqueue Mapping, by the way, because you're still going to have an IO thread that does the IO emulation, and then it sends off the request to yet another thread, that the worker thread in the thread pool. So it's like, it doesn't fit very well, especially on Linux. I recommend using cache equals none and IO native. Okay, so I wish that was it. I wish it was very, very simple, very easy, nothing to do, and it could just automatically enable this feature and always use it when you need it and not use it when you don't need it. But there is some human configuration that's necessary. You need to choose the number of IO threads you want to configure. If you have too few IO threads, what happens? Well, then we end up with a situation like we had with one IO thread where we can't saturate the disk, right? So too few IO threads means your performance won't be as good as you can get. You won't be able to get all the IOPS that the disk can do. If you have too many IO threads configured, then you're kind of wasting those CPUs and they might interfere with your application. You really want to have a small set of IO threads and then use all your other CPUs for the application, which is the actual point of running your VM. So I did benchmarking and I found that usually 4 IO threads works well with local NVMe drives, and this will depend on the type of storage that you use, how fast the drives are, whether it's maybe network storage or whether it's local flash storage. But 4 to 8 is a good starting point, and if you need to get the absolute most out of it, then just run some experiments yourself and see what's best. Another thing is, how do you even assign these IO threads if you have multiple virtio-blk devices? You can actually share the IO threads between multiple devices, so they don't need to be dedicated. And this is a very common use case. Often you might have a system disk or a boot disk with your operating system, and a separate data disk where the actual workload is going to be doing most of its accesses. And in that case, you don't need to have dedicated IO threads just for that boot disk. You can go ahead and share the IO threads. It won't really impact performance because it's a low utilization virtio-blk device that won't interfere. So you have that flexibility. If you want to have multiple virtio-blk devices sharing the same IO threads, you can do that. Okay, and when you have multiple threads, one more thing you can do that will help performance is you can pin them to host CPUs. If you do not pin them, then the Linux scheduler on the host will just run them where it thinks it's convenient to run them. When you pin them, on the other hand, you're telling the scheduler only run them here. And that can help because you can make sure that those host CPUs are not running anything else other than your IO threads. And you're basically dedicating a CPU just to an IO thread. So what this graph shows, the first 4 bars, they are without pinning. The next 4 bars are with pinning. And I tried 1, 2, 4, and 6 IO threads. And what you can see is that with pinning, you get the full performance quicker. And what you can't see here is that when I reran this many times, the no pinning results had more variance. They would change. And that's because with pinning, you just get more reliable results, right? Nothing else is going to interfere, and your IO threads aren't going to be scheduled on different CPUs at inconvenient times. So libvirt has a syntax for doing IO thread pinning. You can just use the IO thread pin tag. The other thing to know about pinning the best place to pin is on the same NUMA node where the physical storage adapter is attached, because you might have a machine where certain PCI slots are on a certain NUMA node. So if your guest RAM is there, pin it there with the storage controller, and that's where you get the best performance. So the final thing about pinning is that if you're using multiple hosts, like in a kind of data center scenario where you have live migration and so on, then you really need orchestration or management tool support for the pinning. If you specify pin to CPU number 8, after you do live migration, you don't know what else is running on the migration destination host on CPU number 8, and you might have multiple things running on there, and you're not really dedicating the CPU. So in order to do pinning in that kind of situation, you need support. If you don't, just don't use pinning for that. Performance won't be quite as reliable or as good, but it's still, IOThread Virtqueue Mapping still helps even when you don't have pinning enabled. Okay, so I've talked about configuration. Let's have a look at some of the benchmark results. So this is a random read 4 kilobyte FIO benchmark on a local Intel flash drive. And what you can see is that, similar to the actual simulation I did in the beginning, we're able to achieve a similar thing. We're able to saturate the disk and get about twice as many IOPS as we had with just one IO thread. So having 4 IO threads is good in this case. So that's nice, but what else do you need to be aware of? Large block sizes. If you have an application that does 64 kilobyte or larger block sizes, you probably won't see the same kind of improvement that we saw with a 4K here. And the reason for that is because you can just send fewer 64K or 256 kilobyte or whatever requests to a drive and saturate it already. So then it's the drive that becomes the bottleneck, and the IO thread, the number of threads you're using doesn't really matter so much. And so maybe even one IO thread will be enough in a case like that. So if that's your workload, then maybe IOThread Virtqueue Mapping isn't very important for you. But if you have a mixed block size workload or a small block size workload, then IOThread Virtqueue Mapping is definitely something to investigate. Okay, another thing I wanted to show you is that the 2x IOPS kind of improvement that I got on my machine is a nice number. But what happens when we run real workloads, bigger workloads, not IO micro benchmarks? My colleague Sanjay Rao at the Red Hat Performance team, he ran HammerDB on Oracle, he ran it on Microsoft SQL Server. And here you can see that when he ran it on 192 vCPU guest. He saw nice improvements, 10 to 20% improvements. But you can already see that as he dials up the workload, the actual improvement decreases. So next, what he tried doing is he tried running 8 instances of the same benchmark on the same host, really packing the host, driving more I/O through it. And then you can see that there's actually the benefits of it go away, and you're basically just in the noise, and there's no benefit. And this is kind of obvious, but the point is that if you have no spare CPU cycles, and if your disks are saturated, this is not going to help you. And the philosophy behind this is that IOThread Virtqueue Mapping, this is not an optimization. It's a feature that allows you to assign more resources to your VM. Okay, so it's not going to make things magically faster. You need to have more resources. If you don't have spare resources to assign to your VM, then your IOPS will stay the same. Okay, so future directions. This is for virtio-blk only at the moment. Virtio-scsi could also be done, but that will need some more work because the QEMU SCSI layer is currently single-threaded. So all the I/O processing has to happen in one thread, and we would need to refactor that to make it work. Another part of this work that can be reused in the future is the IOThread Virtqueue Mapping syntax and some of the thread setup code that we're using on virtio-blk. If you want to implement multiple I/O threads for another device type, say you're doing a user space VirtioNet implementation with multiple queues, and you want to add that to QEMU, today that doesn't exist, It's possible to reuse some of the code. So talk to me, and I'd be happy to chat about some of the things we learned while developing this, and maybe how to do it for other types of devices, non-storage devices. And finally, I just mentioned that this is not an optimization. It's actually just a feature to assign more resources to your virtio-blk device than you could have before. It's still important for us to optimize QEMU, right? There's still all these CPU cycles, this virtualization overhead. And so that's still a good mission, and that's still something that's worth doing. Okay, so to summarize, IOThread Virtqueue Mapping is a virtio-blk feature that improves scalability. It's really designed for IO-intensive workloads. So if you have workloads that have many vCPUs and are driving a lot of IO, you can probably improve your IOPS and reduce the virtualization overhead by trying this out. And I'm also giving this talk here because I also want to let management tool developers and orchestration tool developers know that this feature exists and that you can give this feature to your users if you implement the libvirt syntax or the QEMU syntax that I showed. There's a blog post where you can read more about IOThread Virtqueue Mapping on the Red Hat blog. So check that out if you're interested. All right, thanks.
I want to join the two talks from Kevin and you. Have you tried or thought about using IOThreads in QEMU storage daemons so that you can share the IOThreads across multiple VMs, and so you can basically saturate the disk across multiple VMs?
Yeah. So in QEMU, so QEMU storage daemon, the QEMU tool that uses the QEMU block layer in a separate process, would allow you to have this architecture very similar to SPDK, where you have one daemon running on your host that's doing all the disk I/O. And those I/O threads could then be shared not just between devices for one guest, but all the devices for all the VMs on the host. So that makes sense if you want to dedicate CPUs, PIN, and everything, those kinds of optimizations. Doing them for every single VM can be hard, but if you consolidate everything into one QEMU storage daemon, then that works well. And it is possible. The exports, so in QEMU storage daemon, the exports we have, like vhost, user block, etc., they do support an IOThread parameter. Right now, it only takes one IOThread. It doesn't do IOThread Virtqueue Mapping yet. But this it could be ported now relatively easily to that, I believe. And then we could do that there. So then you could configure your host so that you only have one QEMU storage daemon, say 8 IO threads, and that handles all the IO for all your VMs. Yeah. Yes.
I can. Just two questions quickly. The Oracle database, the HammerDB numbers you were showing, as the number of users went up, the performance went down. Do we understand why that happened?
Yeah, I mean, it's the same scenario I was describing before, where if you push your host more, if you're saturating the host anyway, then there's no spare resources anymore. So
CPU in this case, most likely.
Yes.
That's the assumption that we took the CPU away.
Right.
And that's like submission went down, something like that.
Or maybe the disk, maybe the storage system is saturated anyway. You can't push it any further, so the benefit goes down.
Okay. So yeah, so the second question was, I think is general for the community. Like, is anybody using QST? Like, I'm just trying to get a sense, or plan to use QST or anything. Like, are there any users here? I think that's what my question is. I guess not in this room, at least. Thank you.
Yeah, I noticed that you showed the command line for the multi-queue. This is in JSON syntax. Is there any equivalent in the normal form, like K equals the value?
No. The answer is it was necessary to only use the JSON syntax because QEMU's command line parsing, the normal command line with non-JSON, can't parse nested structures like this.
Okay.
But I mean, for example, libvirt nowadays it uses JSON, and so I think over time the stack, the JSON syntax is becoming more common. But if you're building your own command lines, you would have to use this. It's not too hard to convert, though.
Okay. Yeah. There's maybe some tools for serialization for this command, passing this command line.
Yeah. I mean, another thing you can do is libvirt has a feature to dump the QEMU command line. So you could configure it using libvirt and then see, what does libvirt generate, and you can then use that in your own scripts. Okay,
thank you. My second question. I noticed that there's also for NIC, there's also multi-queue. Do you think the idea for your storage multi-queue can also apply for the NIC?
Oh, absolutely. But most of the time, I think VMs nowadays probably use either vhostnet or maybe vhost user net, and they bypass QEMU. QEMU's device emulation, where we implemented all this, is not used at all. So, yeah.
Okay, thank you.
So I want to thank Christian, who's going to ask the next question. He actually wrote a blog post about this before I even had a chance to publish any information about it. I don't know how he figured it out, but thank you. It was great that you benchmarked it, and thanks.
Yeah, so this was actually, we were trying to find out what can we do to improve performance, and some of our research folks basically found that, and so we tested it. And of course, we are also running into issues right now testing things. And one thing that we saw was that the IOThread polling seems to have still some quirkiness. And I think when we look into the IOThread polling again, especially with this multi-queue, there might be more performance to gain, especially for these larger guests with more CPUs or more guests at the same time. Because that is something where we saw turning polling off improved performance, which was unexpected, for example, and other oddities.
Right. Yeah, it can, if you turn off polling, then the host will respond less quickly, maybe more I/O batches up, and then you're doing more batching, so less overhead per unit of work. So sometimes being slower actually makes things faster.
So I guess there's optimization potential in that regard.
Yeah. Thank you.